Hello and welcome to Whispers of Earth, where wonder meets the night, and science gently guides us through the vast mysteries of existence. Tonight, we embark on a tranquil journey toward one of the most thought-provoking and mysterious questions we face, not just as curious minds, but as human beings contemplating our place beneath the stars. It's a question that has fascinated us all. What is guiding us, and what is the true nature of our connection to the cosmos? Imagine standing beneath the endless sky, looking out at the stars. As you gaze into the vastness of space, the sheer scale of it all feels almost overwhelming. Stars and galaxies swirl, their distant light reaching us across unimaginable distances. The universe is so grand, so intricate, and yet, as we peer into it, there's a haunting emptiness, a sense that something is missing. For centuries, we've looked to the stars for answers, seeking to understand the very fabric of the cosmos. We've unraveled many mysteries: the formation of stars, the birth and death of galaxies, the dance of planets around their suns. But there's a hidden force, a subtle presence, that continues to elude us. It's not visible to the eye, and yet it's there, shaping the universe in ways we are only beginning to understand. This invisible force is what we call dark matter, the mysterious substance that makes up a staggering 85% of the mass in the universe. Yet, we can't see it. We can't touch it. We can't even directly measure it in the conventional sense. And still, scientists have gathered enough evidence to know that it exists. Something is holding the universe together, keeping the galaxies from flying apart as they spin. Something that is not just elusive, but utterly baffling. As we venture deeper into the mystery of dark matter, we begin to ask, what is this force? How does it work? How can something so fundamental be so invisible to us? And what role does it play in the grand cosmic symphony where every star, every planet, and every galaxy seems to move in harmony, bound together by forces we can't fully grasp? In this journey, we will explore the theories, the discoveries, and the ongoing search to uncover the true nature of dark matter. And as we do, we may come to understand that the very fabric of the universe, its structure, its rhythm, and its balance, may be shaped by forces far beyond our current comprehension. As we stand on the edge of discovery, we must first ask, how do we even know that dark matter exists if we can't see it? This is where the true wonder begins, because the story of dark matter is one of observation, theory, and insight that transcends the visible universe. It starts with an unexpected clue, a puzzle piece that didn't quite fit into the well-established model of how we thought galaxies should behave. In the early 1930s, a brilliant astronomer named Fritz Zwicky was studying galaxy clusters. He noticed something strange. Galaxies in these clusters were moving much faster than they should have been, based on the gravitational pull of the visible matter. The stars, gas, and dust that made up the clusters. According to the laws of physics, these galaxies should have been flying apart. not remaining bound together in clusters. Zwicky made a daring conclusion. There must be some unseen force, something invisible, something with mass, that was holding these galaxies together. He dubbed it dark matter. For years, Zwicky's theory was largely overlooked. A fascinating idea, but too speculative to be proven. Yet, as time passed, more and more astronomers began to notice similar anomalies in their observations. Galaxies, it seemed, were moving in ways that defied explanation by visible matter alone. The universe wasn't behaving as we expected. Dark matter, once just a theory, was beginning to gain traction as the best possible explanation. Fast forward to the 1970s, and another astronomer, Vera Rubin, made a discovery that would change the course of our understanding. Rubin was studying the rotation of galaxies, examining how stars moved as they orbited the center of their galaxies. According to the laws of physics, stars on the outer edges of galaxies should have been moving slower than those near the center, as gravity pulls harder on objects that are closer. But what Rubin found was startling. Stars on the outer edges of galaxies were moving just as fast as those near the center. Once again, something was wrong. The only way to explain this anomaly was if there was additional unseen mass in the galaxy. Mass that didn't emit light, heat, or radiation. Dark matter seemed to be everywhere, influencing the motion of galaxies. But we couldn't see it, touch it, or detect it through conventional means. These discoveries set the stage for the ongoing hunt for dark matter. The more we look, the more we realize that it is the unseen hand that holds galaxies, galaxy clusters, and even the vast structures of the universe together. But how? And what is it exactly? Is it a new kind of particle, a new force, or something entirely different? To truly understand dark matter, we must first acknowledge the vast scale of the universe itself. Imagine standing on Earth, looking up at the night sky, and seeing stars scattered across the heavens. Those stars, though brilliant and numerous, are just a fraction of what exists out there. The true vastness of the universe is revealed when we begin to see the immense structures, galaxies, clusters, and superclusters that stretch across billions of light years. But here's the twist. When we observe these structures, we find something puzzling. The visible matter in the universe, everything we can see with our telescopes, from stars to planets, from nebula to black holes, does not add up to the mass we need to explain how these structures hold together. The galaxies move, as we saw with Rubin's discovery, as if they have far more mass than we can account for. And this is where dark matter comes in. Think of it like this. If you imagine a galaxy as a spinning disk, with stars moving in orbits around the center, you expect the outer stars to be moving slower, pulled by the gravity of the mass at the center. However, the outer stars are moving just as quickly as those near the center. It's as though the galaxy has a hidden mass, like a cloak of invisible material that surrounds and holds everything together. This invisible material, this dark matter, is what makes the galaxies behave as they do. The mystery deepens when we look at the universe as a whole. the way galaxies cluster together, the distribution of matter in the universe, and even the expansion of the universe, all seem to suggest that something else is at work, something beyond what we can see. Dark matter, as scientists believe, is the unseen glue that binds everything together. It accounts for the missing mass, giving galaxies the gravitational pull they need to stay intact despite their rapid rotation. But while we've observed its effects, we still have no clear picture of what dark matter is. Is it a new kind of particle? A type of exotic matter we've never encountered? Or perhaps it's a completely unknown form of energy or force that operates in ways we've yet to comprehend. Theories abound, but dark matter remains a profound mystery, one that challenges everything we thought we knew about the universe. As scientists work tirelessly to uncover the nature of dark matter, experiments and theories continue to emerge. From particle accelerators to deep space observations, each new discovery brings us a step closer to understanding the role dark matter plays in the structure and evolution of the universe. Yet, with each new answer, more questions arise, keeping us in a state of awe and wonder. As we continue our journey into the enigma of dark matter, we must take a moment to reflect on how elusive this mysterious substance truly is. Unlike ordinary matter, which interacts with light and can be detected through telescopes and other instruments, dark matter doesn't emit, absorb, or reflect light. It's completely invisible to our current instruments, yet its presence is undeniable. The discovery that dark matter exists isn't a single revelation, but a gradual unfolding. One of the key pieces of evidence for its existence comes from the way galaxies behave. We've already seen how stars on the outer edges of galaxies move as if they're being pulled by something beyond the visible stars and gas. But there's more. Another critical piece of evidence for dark matter comes from observing galaxy clusters. In the 1930s, the same astronomer, Fritz Zwicky, who first proposed the existence of dark matter, observed how galaxies within clusters move. Based on the visible matter in these clusters, the galaxies should have been flying apart due to their rapid motion. However, they remain tightly bound together. The only explanation for this, Zwicky concluded, was the presence of unseen mass, dark matter, acting like the invisible glue that holds these clusters together. But how do we know this is truly dark matter and not something else? One clue lies in the gravitational effects that dark matter has on visible matter. Scientists have used a phenomenon known as gravitational lensing to observe the effects of dark matter. When light from distant galaxies passes through galaxy clusters, the cluster's mass bends the light in such a way that we can actually see the effects of dark matter. By studying the way the light bends, we can map out the location of dark matter in these clusters, even though it remains invisible to our eyes. But this raises the question: what is dark matter made of? What kind of particles could possess mass without emitting light or interacting with electromagnetic forces? Scientists have proposed several theories, one of which suggests that dark matter may be made up of weakly interacting massive particles, or WIMPs. These particles would be very massive compared to normal particles, yet they interact only through gravity and possibly the weak nuclear force, making them extremely difficult to detect. Another possibility is that dark matter could be made of axions, hypothetical particles that are incredibly light and weakly interacting. These particles could potentially be detected through extremely sensitive experiments, but so far, no direct evidence for their existence has been found. Despite these ideas, the truth about dark matter remains elusive. We've observed its effects in many ways, but we still don't know exactly what it is. Yet this mystery drives scientists to push the boundaries of their understanding, seeking answers in places far beyond what we can see, and exploring realms of physics that challenge our current theories. As we continue to explore the possibility of dark matter, one question becomes increasingly urgent. How does it fit into the larger structure of the universe? We know that dark matter holds galaxies and galaxy clusters together, but its influence extends even further, shaping the very fabric of the universe itself. In fact, dark matter might be responsible for the large-scale structure of the cosmos. Imagine the universe as a vast, intricate web. Ordinary matter, the stars, planets, and gas that we can see, forms the visible nodes of this web, the clusters and galaxies scattered across the void. But dark matter is the thread that holds everything together, creating a vast, invisible network that governs the overall structure of the cosmos. Without it, galaxies would fly apart, and the delicate balance of gravitational forces would collapse. Dark matter, in this sense, acts like the skeleton of the universe, giving it shape and stability. To understand this better, let's turn to simulations of the universe's evolution. When we model the formation of galaxies and large cosmic structures, dark matter plays a crucial role. In these simulations, dark matter forms vast clumps, which in turn attract ordinary matter, helping to create the galaxies and clusters we see today. Without the presence of dark matter, these structures would never have formed. The universe, instead of being a web of interconnected galaxies, might have remained a chaotic void with matter scattered randomly. In a sense, dark matter is the invisible hand that has sculpted the universe into the grand, structured cosmos we observe. It's the reason why galaxies exist in clusters and why these clusters are arranged in superclusters. It's why the universe has the shape it does. The presence of dark matter throughout the cosmos has shaped its evolution over billions of years, creating the galaxies, stars, and planets that allow life to exist. But while dark matter's role in the formation of large-scale structures is becoming clearer, there is still much we don't know. One of the most intriguing questions is how dark matter interacts with itself. Does it collide with other dark matter particles, or does it simply pass through them, never interacting except through gravity? Some theories suggest that dark matter might not be a single uniform substance, but could be made up of different types of particles that interact with each other in complex ways. Another question is whether dark matter could play a role in the formation of the very first galaxies. The earliest galaxies in the universe formed just a few 100 million years after the Big Bang. Dark matter was likely the key factor in this early formation, helping to collapse gas clouds and create the dense regions where stars first ignited. Without dark matter, it's possible that these early galaxies would have never formed, and the universe would have remained a much emptier place. As we peer deeper into the cosmic web, the realization dawns that dark matter may not just shape the universe's structure, but also influence the very nature of its expansion. While dark matter is known for holding galaxies and clusters together, its relationship with dark energy, the force believed to be driving the accelerated expansion of the universe, adds yet another layer of complexity to the cosmic puzzle. Imagine the universe as a balloon, its fabric stretching as it inflates. This expansion, which began with the Big Bang, continues today, with galaxies moving away from each other at an ever-increasing rate. Dark energy, the mysterious force responsible for this accelerated expansion, is pushing the universe apart. But what role does dark matter play in this? How does it influence the expanding fabric of the cosmos? At first glance, dark matter and dark energy might seem to be opposing forces, one pulling everything together, the other pushing everything apart. But recent studies suggest that their relationship may be more subtle than we initially thought. Dark matter doesn't just shape galaxies. It also affects the rate at which the universe is expanding. Its gravitational pull, combined with the effects of dark energy, creates a delicate balance that governs the fate of the universe. In the early universe, dark matter played a critical role in slowing down the initial expansion after the Big Bang. As matter cooled and began to clump together, the gravitational pull of dark matter helped slow down the rate of expansion, allowing galaxies and stars to form. Over time, however, dark energy became more dominant, pushing the universe to expand faster and faster. The interplay between these two forces, dark matter's gravitational pull and dark energy's expansionary force, is one of the most profound questions in modern cosmology. This tension between dark matter and dark energy is central to the question of the universe's ultimate fate. Will the forces of dark matter one day slow down the expansion of the universe, causing it to collapse in on itself in a big crunch? Or will the acceleration driven by dark energy continue indefinitely, causing the universe to expand forever, stretching the fabric of space-time to its limits? These are the cosmic questions that dark matter and dark energy challenge us to answer as we continue to search for their true nature. For now, the role of dark matter in the universe's expansion remains one of the most intriguing and mysterious aspects of cosmology. It is clear that dark matter is not just a passive component of the universe, but an active participant in shaping its future. As we continue to explore the vast, unseen influence of dark matter, a new question arises. Could dark matter hold the key to unlocking the very laws of physics? We know that ordinary matter, the kind we are made of, interacts through gravity, electromagnetism, and the strong and weak nuclear forces. But dark matter, as we've seen, interacts only through gravity and possibly the weak nuclear force. It doesn't emit, absorb, or reflect light, making it incredibly difficult to study. Yet, by understanding dark matter, we may unlock the mysteries of physics itself. The search for dark matter is more than just a quest to understand a mysterious substance. It's a pursuit to expand our understanding of the universe's fundamental laws. Dark matter doesn't behave like anything we've encountered in the visible universe, suggesting that there may be other, unknown forces at play. Could dark matter represent a new type of particle or force that exists beyond the current framework of particle physics? The hunt for dark matter particles has led scientists to propose several intriguing possibilities. One of the leading candidates for dark matter particles is the weakly interacting massive particle, or WIMP. These particles are thought to be heavy, but they interact with regular matter only very weakly. WIMPs are one of the most promising explanations for dark matter. But despite extensive efforts using particle accelerators and detectors, no direct evidence of their existence has been found yet. Scientists are building more sensitive experiments, hoping to detect the rare interactions of WIMPs. But the question remains, are WIMPs the answer? Or is there something even more mysterious at play? Another possibility lies in actions, hypothetical particles that are very light and weakly interacting. These particles could account for dark matter in a completely different way. Unlike WIMPs, axions would be much less massive, potentially even lighter than electrons, and would interact with other particles via very weak forces. Their properties make them even harder to detect, but they remain a strong candidate for dark matter. And then there's the theory of self-interacting dark matter. If dark matter particles could interact with each other in ways that were previously thought impossible, this could provide insights into the behavior of galaxies, the formation of cosmic structures, and even the behavior of gravity itself. In this model, dark matter could act more like a fluid than a collection of individual particles, offering a new perspective on how galaxies and galaxy clusters hold together. Understanding dark matter means challenging the very fabric of physics. If we can detect and understand dark matter's true nature, we will not only answer one of the greatest mysteries of the cosmos, but also open the door to new physics, possibly revealing unseen forces that govern the universe. Tonight, let's move gently from theories to the quiet clues the universe leaves for us. Traces of an invisible presence written in light and gravity. Astronomers sometimes call it seeing the unseen by the shadows it casts. Not shadows of darkness, but of gravity. When the glow from a distant galaxy travels toward us, it can pass through a massive cluster on the way. The cluster's gravity bends that light, curving it into arcs and smudged rings, like glass rippling over a candle flame. This gravitational lensing lets us map where mass truly is, and again, the maps point to something more than stars and gas, vast halos of matter that don't shine, draped around galaxies like invisible cocoons. In some galaxy clusters, nature has staged an even clearer demonstration. Two clusters pass through each other like ships in a fog. The hot gas, ordinary matter, slams together and slows, heating and glowing in X-rays. But the gravity map tells a different story. Most of the mass glides ahead, barely interacting, as if made of particles that pass through one another without a fuss. The light bends where that mass goes, not where the glowing gas lingers. It's a quiet, elegant sign. Something unseen holds most of the weight. The afterglow of the Big Bang, an ancient, whisper-thin light called the cosmic microwave background, adds another clue. Tiny ripples in that early light form a kind of fingerprint for the whole universe. When we read that print, we learn proportions. Ordinary matter is only a small slice. Dark matter outweighs it by several times, helping gravity sculpt the first knots and filaments that later became galaxies. Without that extra gravitating material, the cosmic web would have woven far more slowly, perhaps too slowly for a sky like ours. None of this shows us what dark matter is. It shows us what it does. It bends light without shining. It carries mass without colliding. It guides structure without glowing. Down on Earth, in quiet underground labs, detectors sit like patient night watchmen, listening for the faintest tap from a passing dark particle. So far, the silence persists. But even silence can be instructive. It narrows the possibilities, teaches us where not to look, and how to listen more carefully. For now, we can rest in what the universe is willing to show. Arcs of lensed starlight, drifting cluster cores, and a fossil glow from the beginning, all pointing toward an unseen scaffolding. We don't need to chase it tonight. We can simply acknowledge its embrace, the way it holds galaxies together and us within this vast and ordered night. As we continue this quiet journey through the cosmos, we begin to appreciate how dark matter, though invisible, plays a vital role in shaping the universe. Yet, while its gravitational influence is clear, the essence of dark matter remains elusive. Could it be that the key to understanding dark matter lies not in what it is, but in what it does? Its impact on the grand cosmic structure. One of the most captivating aspects of dark matter is its role in shaping the very architecture of the universe. Imagine the universe as a grand, intricate web, a cosmic tapestry stretching across billions of light years. Every thread in this web is a galaxy, held together by the invisible hand of dark matter. Without it, galaxies wouldn't have the mass needed to bind their stars together. There would be no cosmic clusters, no galactic filaments stretching across space. Instead, the universe would remain a chaotic expanse of scattered stars, without the elegance and order we observe today. Dark matter's ability to bind galaxies and clusters together is, in a sense, an expression of its power. It doesn't interact with light, nor does it engage with the electromagnetic forces that govern our daily world. But through gravity, it pulls everything toward it, drawing galaxies into clusters, shaping the larger structure of the universe as it grows. This subtle, unseen force allows for the formation of galaxies, and without it, we would never have the beautiful, organized patterns we see today. As we gaze upon these vast structures, from clusters of galaxies to the intricate filaments of the cosmic web, we begin to appreciate the deep, invisible threads that bind the universe together. Dark matter is not just an enigmatic substance that fills space. It is the very foundation upon which the universe's grand design rests. Its presence is felt in every corner of the cosmos, shaping everything from the smallest galaxies to the largest superclusters. Yet, for all its importance, dark matter remains a mystery. We've never directly detected it, and its true nature is still beyond our understanding. But perhaps that's what makes it so fascinating. The more we learn, the more we realize how much there is yet to discover. It is a reminder of the limits of our knowledge and the endless possibilities that lie ahead. The pursuit of dark matter is not just about uncovering a new substance, but about deepening our understanding of the universe itself, the invisible forces that govern everything, and the cosmic dance that binds us all. As we continue to venture through this cosmic journey, it becomes evident that dark matter is not merely a passive presence in the universe, but an active force that shapes the very fabric of space-time. Though we cannot touch or see it directly, the influence of dark matter is felt in ways that are undeniable. In many ways, dark matter seems to act like the skeleton of the universe, giving structure to the sprawling cosmic expanse. It binds galaxies and clusters together, sculpting the large-scale structure of the cosmos, yet remains entirely hidden from our senses. If we imagine the universe as an immense, sprawling city, dark matter would be like the unseen foundation beneath every building. It is what holds the walls of galaxies together, what prevents the sprawling city of stars from falling apart. Without this hidden force, the stars in our galaxies would drift away, and the beautiful cosmic structures we observe would disintegrate. The stars that shine so brightly in the night sky would be scattered like dust, without the gravitational glue provided by dark matter. The structure of the universe as we know it would be vastly different without the presence of dark matter. It is not only the binding force between galaxies, but also the reason why clusters of galaxies hold together despite their sheer size and mass. Without dark matter's gravitational influence, galaxies would not have the mass necessary to form and maintain their shapes. The universe's vastness would feel like a vast, empty void, with no structure to hold everything in place. But how did dark matter come to be? Where did it come from? And why does it interact with gravity, but not with light or other known forces? These are the questions that continue to challenge scientists today. The presence of dark matter was first hypothesized to explain the unexpected gravitational effects seen in galaxy clusters. But now, we know it is everywhere. It permeates the vast stretches of space, invisible but essential to the cosmic dance. As we delve deeper into the unknowns of dark matter, we must confront the possibility that the universe itself may be far stranger and more mysterious than we ever imagined. Could there be other forces at play in the cosmos? Forces that we have yet to discover, that operate outside of the known laws of physics? The search for dark matter is not just a quest for an unseen substance, but a journey into the unknown reaches of the universe, a reminder that there is still so much more to learn about the nature of reality. As we continue to delve deeper into the cosmic fabric, one thing becomes increasingly clear. Dark matter is not just a key to understanding the universe's structure, but a puzzle piece that may unlock secrets about the very nature of existence itself. If dark matter shapes the galaxies and clusters we observe, what does that say about the fundamental forces of the cosmos? And could understanding dark matter lead us to a deeper understanding of the universe's origin and its ultimate fate? At its core, dark matter challenges everything we thought we knew about the universe. It defies our expectations of what matter should be. Ordinary matter, the kind we encounter daily, interacts with light and other forms of energy, allowing us to observe and measure it with instruments. Dark matter, however, does not interact with light at all. It's invisible, detectable only through its gravitational pull. This fundamental difference raises important questions. Why is dark matter so different from the matter we know? How can something so pervasive remain so elusive? And what does it mean for our understanding of the universe if our fundamental concepts of matter and energy are incomplete? One way to explore these questions is by considering how dark matter might help us understand the universe's origin. The most widely accepted theory of the universe's creation, the Big Bang, suggests that the universe began as an infinitely small, hot, and dense point that rapidly expanded, giving birth to all the matter and energy we observe today. But the existence of dark matter implies that there was something else involved in this creation, something beyond the visible matter that formed in the aftermath of the Big Bang. Some cosmologists theorize that dark matter could have played a crucial role in this early expansion. In the moments after the Big Bang, the universe was a swirling, chaotic mass of energy and particles. The presence of dark matter could have helped to slow the rapid expansion of the early universe, allowing matter to condense and form galaxies, stars, and planets. Without dark matter's gravitational influence, the universe might have expanded too quickly, preventing the formation of the complex structures we see today. The mystery of dark matter also forces us to reconsider the very nature of gravity. Gravity is one of the four fundamental forces of nature, but it behaves differently in the presence of dark matter. Its influence is felt more strongly in galaxy clusters, where it holds galaxies together despite their rapid motion. Could this suggest that gravity itself is a more complex force than we understand, one that interacts with unseen substances in ways that have yet to be fully explained? As scientists continue to investigate dark matter, it becomes clear that the answers to these questions may not only reshape our understanding of the universe, but also challenge our very understanding of reality. What we are discovering is that the universe is not simply a collection of visible objects and forces, but a far more intricate and mysterious place. Dark matter, as elusive and invisible as it may be, is teaching us that there is more to the cosmos than meets the eye. As we reach deeper into the mystery of dark matter, it's impossible not to consider the profound implications it may have for our understanding of the universe's very structure. If dark matter is responsible for binding galaxies and galaxy clusters together, could it also be the key to understanding the elusive nature of gravity itself? Could dark matter be a reflection of something beyond the known laws of physics, challenging the very fabric of our scientific theories? One of the most remarkable aspects of dark matter is that it doesn't just shape the large-scale structure of the universe. It also interacts with gravity in a way that could provide clues to understanding the nature of this fundamental force. Gravity, as we know, is the force that governs the motion of planets, stars, and galaxies. But how it works on the grand scale of the universe is still a bit of a mystery. In fact, gravity is the weakest of the four fundamental forces in nature, yet it is the most dominant on the cosmic scale. The mystery deepens when we consider how dark matter interacts with the force of gravity. On Earth, gravity is straightforward. It pulls objects toward one another based on their mass. But in the cosmic realm, where dark matter exists, gravity behaves in peculiar ways. Dark matter doesn't emit or absorb light, yet it has mass, which means it exerts gravitational pull on both visible matter and other dark matter particles. This allows dark matter to create gravitational wells that warp space and time, much like the gravity of stars and black holes does, yet without being detectable through light or radiation. This strange and invisible nature of dark matter challenges our current understanding of how gravity operates on the largest scales. It hints at the possibility that gravity may be more complex than we've realized. Could dark matter be part of a more intricate version of gravity that extends beyond the simple models we've built? What if the gravitational forces we observe in galaxies and clusters aren't just a product of visible matter, but a result of an entirely new form of gravitational interaction? One that is still hidden from our view? As we continue to probe the mysteries of dark matter, scientists are beginning to ask even bigger questions. Does dark matter represent a new kind of particle, one that interacts with other forces in ways we've never imagined? Or is dark matter a manifestation of some unknown aspect of gravity itself? The discovery of dark matter and the ongoing search to uncover its true nature may ultimately lead us to a deeper understanding of gravity and the fundamental forces that govern the universe. The search for dark matter is not just about finding one missing piece of the puzzle. It's about revising the entire picture of how the universe works, from the ground up. Every new discovery in the study of dark matter opens up new avenues of inquiry, allowing us to peer deeper into the mysteries of space, time, and gravity. And with each step forward, we inch closer to uncovering the true nature of the forces that hold the universe together. As we continue our exploration, one thing becomes increasingly clear. Dark matter is far from a simple enigma. Its role in the universe is as profound as it is mysterious, yet it may hold the answers to some of the most fundamental questions in physics. The more we discover, the more we begin to see that dark matter's influence may not be limited to just galaxies and clusters. Could dark matter also be the key to understanding the universe's expansion and perhaps its eventual fate? If we zoom out from our study of galaxies and clusters, we begin to consider the entire universe, stretching back to the Big Bang itself. In the first moments after the universe was born, it expanded rapidly in what we call inflation. During this time, the universe grew from subatomic scales to immense proportions in the blink of an eye, and everything, from the formation of atoms to the birth of stars, began. However, dark matter's role in this early expansion could have been more than just structural. It may have helped shape the universe's initial growth too. Scientists believe that dark matter may have played a critical role in slowing down the universe's initial expansion. After the burst of inflation, the expansion slowed, but dark matter's gravitational influence might have caused the universe to cool at just the right rate, setting the stage for the formation of the first stars and galaxies. Dark matter might have even been involved in creating the first cosmic seeds, the initial clumps of matter that would later collapse into galaxies. If the universe had expanded too rapidly, these clumps of matter would never have had a chance to form, and the universe would have looked very different. This balance between the forces of dark matter, dark energy, and the visible matter we can see, all plays a role in the ongoing expansion of the universe. And so, while dark matter may be invisible to our senses, its gravitational effect is deeply woven into the fabric of the cosmos, controlling how galaxies cluster and how structures form in the vast expanse. More than just the invisible glue of galaxies, dark matter could be the force that shapes the very destiny of the universe itself, influencing the balance between expansion and collapse. Yet, even as we begin to unravel the role of dark matter in the universe's birth and expansion, many questions remain. Why does dark matter behave in such an unusual way? Why does it only interact with gravity and not with light or electromagnetism? And perhaps most intriguing of all, could dark matter be connected to the even more mysterious concept of dark energy, the force responsible for the accelerated expansion of the universe? As we reflect on dark matter's profound influence, one of the most compelling aspects of this elusive substance is its relationship with dark energy, the mysterious force that is driving the accelerated expansion of the universe. While dark matter is known to exert gravitational pull, dark energy works in the opposite direction, pushing galaxies farther apart as the universe continues to expand at an accelerating rate. The interplay between these two cosmic forces is one of the most mind-bending puzzles in modern science. In the early stages of the universe, shortly after the Big Bang, both dark matter and dark energy played pivotal roles in shaping the cosmos. For billions of years, dark matter dominated the gravitational landscape, pulling matter together to form galaxies, stars, and other cosmic structures. It's likely that without dark matter, the universe would never have reached its present state, as gravity alone, without the invisible matter, would have been too weak to form the structures we observe today. However, around 5 billion years ago, something changed. the influence of dark energy began to overpower that of dark matter. Dark energy, which is thought to account for about 6% of the universe's energy content, began to accelerate the expansion of space. The more the universe expanded, the more dark energy came to dominate, pushing galaxies farther apart. This shift in dominance has profound implications for the future of the universe, making dark energy one of the most mysterious and intriguing forces we've ever encountered. The relationship between dark matter and dark energy is something that physicists are still working to understand. Both are invisible to our current instruments, yet their effects are clearly observable in the motions of galaxies and the large-scale structure of the universe. Could these two forces be related in ways that we haven't yet discovered? Are they two sides of the same coin, one pulling inward, the other pushing outward? And how might they shape the ultimate fate of the universe? Will the universe continue to expand forever? Or could the forces of gravity and dark matter eventually slow it down, leading to a cosmic collapse? These questions are at the forefront of modern cosmology. Scientists are racing to develop new theories and experiments to understand how dark matter and dark energy interact, and how they might influence the evolution of the universe in the future. Understanding these forces could unlock not only the secrets of the cosmos, but also provide a deeper insight into the fundamental laws of physics, offering us a glimpse into the very fabric of reality itself. As we continue our journey through the vast, unseen forces of the universe, it's important to recognize that dark matter may not only be crucial for understanding the structure and expansion of the cosmos, but could also play a role in answering deeper questions about the fundamental nature of reality itself. What if dark matter holds the key to unifying the forces of the universe? Gravity, electromagnetism, the strong force, and the weak force, into a single theory that can explain everything from the behavior of galaxies to the interactions of subatomic particles. One of the most ambitious goals in modern physics is to find a theory of everything, TOE, a single unified theory that can describe all the forces and particles in the universe. For decades, scientists have struggled to reconcile the two pillars of modern physics: general relativity, which explains the force of gravity on large scales, and quantum mechanics, which governs the behavior of subatomic particles. These two theories work incredibly well in their respective domains, but they don't mesh together seamlessly. Could dark matter be the missing link that connects them? Some physicists have proposed that dark matter could be composed of particles that exist within the realm of quantum mechanics, interacting in ways we cannot yet fully comprehend. If dark matter is made of particles that interact only weakly with ordinary matter, perhaps it's revealing a new aspect of quantum physics, one that's hidden from our current understanding. By studying the behavior of dark matter and its effects on visible matter, scientists might be able to bridge the gap between the quantum and the cosmic, providing the elusive connection needed for a theory of everything. Moreover, the role of dark matter in the formation of galaxies and large-scale cosmic structures could offer clues about the earliest moments of the universe. If dark matter played such a significant role in shaping the universe's evolution, could it have also influenced the formation of the fundamental laws of physics themselves? Understanding dark matter might allow us to peer deeper into the origins of space-time, uncovering how the universe came into existence, how the forces of nature emerged, and how everything in the cosmos is interconnected. As we explore dark matter's potential to unify the forces of physics, we also find ourselves at the crossroads of science and philosophy. For centuries, humanity has sought to understand the origins of the universe, the forces that govern it, and our place within it. Dark matter, this invisible substance that influences the very structure of the universe, could be the key to unraveling not just the mysteries of space, but the deeper questions about the nature of reality itself. We're on the brink of discovering something that could fundamentally alter our understanding of the cosmos, a revelation that may forever change our conception of how the universe works and how we relate to it. As we delve deeper into the cosmic web of dark matter and its connection to the fundamental forces of the universe, one truth becomes increasingly clear. The discovery of dark matter is not just about identifying a new substance, but about defining our understanding of the cosmos itself. This elusive, invisible force may be the key to unlocking some of the greatest mysteries of the universe, from the birth of galaxies to the very nature of space and time. Yet, as scientists continue their search for dark matter, they are faced with a perplexing question. How can we study something that doesn't interact with light or other forms of energy? For most of the 20th century, dark matter remained a concept, a theoretical answer to an observed problem. But now, after decades of research and observation, the evidence for its existence is overwhelming. So what happens next? How do we uncover the secrets of a substance that, by its very nature, resists detection? One approach scientists are taking is to look for dark matter's indirect effects. While dark matter itself does not emit or absorb light, it still exerts gravitational forces on visible matter. By observing the motion of stars, gas clouds, and entire galaxies, we can infer the presence of dark matter based on how these objects move. The rotation curves of galaxies, as we've seen before, reveal that there is far more mass than we can account for with visible matter. Similarly, gravitational lensing allows us to map the presence of dark matter by observing how light bends as it passes through clusters of galaxies. But indirect evidence alone is not enough. Scientists are pushing the boundaries of technology, building specialized detectors to hunt for dark matter particles directly. These experiments, many of which are located deep underground to shield them from cosmic radiation, are designed to detect the faintest interactions between dark matter and normal matter. The hope is that one day, these experiments will capture the first direct evidence of dark matter, offering a breakthrough that could revolutionize our understanding of the universe. Yet, even if dark matter is finally detected, we must ask, what does this discovery mean for the future of physics? Will it lead to the discovery of new forces or particles that challenge our current models? Could dark matter be the key to unlocking the mysteries of gravity, space-time, and even the origins of the universe itself? The answers to these questions could reshape the very foundation of science and provide insights into the most profound aspects of reality. The search for dark matter, in essence, is a search for the unknown, a quest to push the boundaries of human knowledge and unlock the deepest mysteries of the universe. As we explore the unseen and the invisible, we are reminded that the universe is not a static, fully understood entity. It is a dynamic, ever-evolving puzzle, with each discovery leading to more questions, and with every question bringing us one step closer to understanding the vastness of the cosmos. As we continue our exploration of dark matter, we are drawn into a larger question. What does the future of dark matter research hold for us? After decades of indirect evidence and years of experimental efforts, the search for dark matter is at a crossroads. With new technologies and greater understanding, we stand on the brink of possibly discovering something that could change the very foundations of physics. The hunt for dark matter has already led to astonishing technological advancements. Particle detectors, sensitive to the faintest interactions between dark matter and ordinary matter, have been placed in the deepest parts of the Earth to shield them from any interference. These experiments, such as the Large Hadron Collider, LHC, at CERN, or the underground labs of the Super-CDMS and Lux-Zeppelin projects, are fine-tuned to detect particles that could very well unlock the secrets of the universe. These experiments aim to directly detect dark matter particles, and while none have succeeded so far, they have already begun to narrow down the possibilities. The absence of certain particles in these detectors helps rule out particular theories, moving scientists ever closer to a potential breakthrough. In a way, each experiment, each failed detection, brings us closer to understanding what dark matter is, even if it seems like we are moving forward in the dark. But if we do eventually detect dark matter, what will that discovery mean for our understanding of reality? How will it affect our view of the universe's origin, its fate, and our place within it? The implications could be profound. First, detecting dark matter would reshape the standard model of particle physics. Currently, the standard model explains all known fundamental particles and forces, except gravity, which is described by general relativity. Dark matter is thought to be made of particles that don't interact with light. But if we detect them, it would mean a new class of particles exists. Particles that we never thought to look for, and particles that would open up entirely new fields of study. Secondly, understanding dark matter could reveal new insights into the formation of galaxies. If we discover the precise nature of dark matter particles, we could finally understand the process by which dark matter shapes the universe. It might explain not just the cosmic structures we observe today, but also offer clues into the early universe, into the formation of the first stars and galaxies. Furthermore, understanding dark matter might lead to breakthroughs in understanding gravity itself. If dark matter interacts only through gravity, this could suggest a deeper, hidden nature to gravity, one that we've only begun to scratch the surface of. Could this be the key to understanding quantum gravity and perhaps unifying all the forces of nature into a single theory? The discovery of dark matter might also force us to confront more existential questions about the universe's fate. With dark matter and dark energy shaping the expansion of the cosmos, the two forces may be linked in ways we can't yet comprehend. Will dark matter and dark energy continue their cosmic dance, driving the universe toward an eventual end? Or will new discoveries lead us to a more hopeful view of the universe's future? As we move forward in our journey to understand dark matter, we begin to explore the possibility that this invisible substance could unlock answers to even more fundamental questions. Questions about the beginning and end of the universe. If dark matter is indeed the glue that holds galaxies together, could it also provide insight into the very origins of the cosmos itself? One of the most intriguing ideas surrounding dark matter is that it may have played a crucial role in the early universe. Just moments after the Big Bang, the universe was an incredibly dense, hot, and chaotic place, full of energy and matter in its purest form. As it began to expand and cool, dark matter could have been the catalyst for the formation of the first structures in the universe. The gravitational pull of dark matter may have helped collapse gas clouds, ultimately giving birth to the first stars and galaxies. In this way, dark matter might be more than just a bystander to cosmic events. It could be the force that shaped the very fabric of the universe in its early stages. If dark matter was responsible for the formation of galaxies, it raises an exciting possibility. Could dark matter also play a role in shaping the future of the universe? There are several theories that suggest dark matter could influence the universe's ultimate fate. One possibility is that the presence of dark matter could lead to a dramatic Big Crunch, in which the universe's expansion slows down and reverses, causing everything to collapse back in on itself. This would create a cataclysmic event, where all matter and energy are compressed into an incredibly dense point, potentially marking the end of the universe as we know it. On the other hand, the influence of dark energy, the force that is driving the accelerated expansion of the universe, suggests that the universe could continue to expand indefinitely. In this scenario, dark matter and dark energy are engaged in a cosmic tug-of-war, with dark energy pushing everything apart while dark matter tries to hold it all together. The outcome of this struggle remains uncertain, and scientists are working hard to determine which force will ultimately dominate. Yet, despite the tantalizing possibilities, we still know very little about the true nature of dark matter. Could it be a remnant from the very beginning of the universe, a remnant from the Big Bang itself? Or could it be an entirely new form of matter, one that transcends our current understanding of physics? As we gather more data from experiments and observations, each new discovery inches us closer to an answer, but the true nature of dark matter remains just out of reach. As we ponder the role of dark matter in shaping the universe's past and future, we begin to realize that its mysterious nature might be the key to unlocking some of the deepest questions in cosmology. But while we continue to search for direct evidence of dark matter, we must also consider the broader implications of its existence on our understanding of the laws that govern reality itself. One of the most striking questions raised by dark matter is whether it could hold the answers to unifying the fundamental forces of nature. For centuries, scientists have sought a way to combine the four known forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, into a single, unified theory of everything. The discovery of dark matter may be the missing piece that connects these forces and leads to a more complete understanding of how the universe operates. Gravity, as we know it, is the weakest of the four forces. Yet it governs the large-scale structure of the universe. The strong and weak nuclear forces rule over the subatomic world, while electromagnetism governs the behavior of charged particles. But dark matter doesn't behave like ordinary matter. It only interacts with gravity and, potentially, the weak nuclear force. And that fact could suggest that dark matter particles might interact with these forces in ways we've never imagined. Could dark matter provide a bridge between these separate realms of physics, offering us a new pathway toward the elusive theory of everything? This question leads us into the realm of particle physics, where dark matter's nature might not only reveal new particles, but could also reshape our current understanding of the universe's structure. The search for dark matter particles, such as WIMPs, weakly interacting massive particles, or axions, has already expanded the field of physics into new territory, where theories once considered speculative are now taken seriously. These hypothetical particles could challenge our established models and lead to the development of entirely new frameworks for understanding the universe. If dark matter does interact with gravity in ways we don't yet understand, it could also change our perception of space-time itself. Dark matter's influence on the motion of galaxies and the formation of cosmic structures hints at the possibility that there are hidden dimensions or forces operating beneath the surface of our observable reality. Could dark matter be connected to higher dimensions, or could it be part of a multi-dimensional space that we have yet to perceive? The answers to these questions could fundamentally alter our understanding of not just the universe, but the very nature of existence. Dark matter may very well be the key that unlocks a deeper understanding of the laws that govern our reality. It serves as a reminder that the universe is still full of mysteries, some of which may forever remain just beyond our grasp, while others may lead us to discoveries that completely rewrite the history of science. As we continue to explore the mysteries of dark matter, the idea that it could unlock a new chapter in the story of the universe takes on a deeper significance. Dark matter is the cosmic riddle that may guide us toward understanding not just the structure of the universe, but the very origins of space and time. It is an invitation to think beyond the limitations of current science, to venture into a realm of possibility that challenges everything we thought we knew about the forces that govern the cosmos. One of the most profound questions we must ask as we explore dark matter is how it might change our understanding of the very beginning of the universe. The Big Bang Theory tells us that the universe began as a singularity, an infinitely small, hot, and dense point, expanding rapidly into the vast cosmos we see today. But what was the nature of that singularity? Could dark matter have existed even in those early moments, playing a crucial role in the universe's birth? If dark matter was present from the very beginning, it could have influenced how the universe expanded and evolved. The early universe was filled with energy and radiation, but as it cooled, dark matter's gravitational pull would have shaped the formation of galaxies, stars, and planets. The invisible matter might have been the scaffolding that allowed visible matter to condense and form into the complex structures we observe today. Perhaps in its earliest days, the universe was more interconnected than we can imagine, with dark matter serving as a hidden thread that bound everything together. As it settled into the gravitational wells of galaxies, dark matter allowed the first stars to ignite, creating the very conditions necessary for life to emerge. The birth of the first galaxies, and the delicate balance between dark matter and visible matter, could be the foundation of everything that followed. The creation of stars, planets, and eventually the conditions that allowed life to flourish on Earth. But what does this mean for the future of the universe? Will the same forces that dark matter helped set into motion continue to shape the cosmos? Or is there a deeper, hidden force that we have yet to discover? The future of dark matter research will likely bring us closer to answering these questions, and may reveal a new understanding of the universe's fate. As dark matter continues to elude direct detection, we are reminded of the vastness of what we still don't know. It invites us to reflect on the limits of human knowledge and the endless possibilities that lie beyond. If we can uncover the true nature of dark matter, it may not just change our understanding of physics, it could transform the way we view our place in the universe. We are standing on the edge of discovery, poised to understand a force that has shaped the cosmos since its inception and could continue to play a role in its evolution. As we continue to grapple with the mysteries of dark matter, we are reminded that the universe is not a static, fully understood entity. It is dynamic, ever-changing, and filled with forces that we are only beginning to comprehend. Dark matter, despite its elusive nature, plays a pivotal role in shaping the universe's structure, and understanding it could unlock answers to some of the most profound questions in cosmology. One of the questions that arises when we consider dark matter is how it fits into the larger picture of the universe's evolution. We know that the universe has been expanding ever since the Big Bang, but how does dark matter influence this expansion? While the presence of dark energy has been linked to the accelerated expansion of the universe, dark matter's role is less clear. Could it be that dark matter is actively shaping the speed at which the universe expands? And how does it interact with dark energy to produce the current cosmic balance? A fascinating possibility is that dark matter and dark energy could be part of a larger, yet-to-be-discovered framework that governs the universe's expansion. While dark energy is pushing galaxies apart, Dark matter could be the counterbalance, working in subtle ways to slow the expansion or influence the formation of cosmic structures. The tug-of-war between these two forces, dark matter pulling everything together and dark energy pushing it apart, could ultimately determine the fate of the universe. This interplay between dark matter and dark energy raises another question. What happens when these two forces reach an equilibrium? Could there come a time in the distant future when the expansion of the universe slows down or even reverses? Could dark matter play a role in preventing the universe from expanding forever, leading to a dramatic cosmic event, a big crunch where everything collapses back into a singularity? The fact that we don't have answers to these questions is a testament to how much we still have to learn about the universe. Dark matter has provided us with a glimpse into the unseen forces that shape our world, and its study has already led to exciting new ideas in physics. But we are still only scratching the surface of what dark matter might be and how it fits into the larger cosmic picture. As we continue to seek answers, we are reminded that science is not just about finding the answers we seek. It's about the journey of discovery itself. Each new step forward in understanding dark matter brings us closer to understanding the very fabric of the universe. And in doing so, it invites us to consider the profound mysteries that still await us, urging us to keep searching, questioning, and exploring. As we delve deeper into the role of dark matter in shaping the universe, we begin to explore its potential link to one of the most fundamental questions in physics. Is the universe infinite, or is it finite, with a definite beginning and end? This is a question that has puzzled scientists and philosophers alike for centuries. The discovery of dark matter may offer clues that could help us answer it. Dark matter's influence on the structure and expansion of the universe suggests that the universe is not just a random collection of matter, but a carefully organized system with hidden rules that govern its development. As we study the behavior of galaxies and clusters, we see that dark matter holds these systems together, giving them stability and shape. But this raises another question. If dark matter is holding galaxies together, what is holding the entire universe in place? What is preventing the universe from collapsing under the force of gravity or expanding too quickly due to the influence of dark energy? In the quest to understand the ultimate fate of the universe, dark matter could play a central role. Some theories suggest that dark matter could be the key to understanding the universe's ultimate fate. Whether it will continue to expand forever, eventually slow down and collapse, or reach some kind of equilibrium. This could be the next step in our understanding of the universe's past, present, and future. Imagine that dark matter is not just a passive substance, but an active force that is helping to guide the universe's evolution. It may be that dark matter is not only the glue that holds galaxies together, but also the force that governs the overall structure of the cosmos. If this is true, understanding dark matter could lead to breakthroughs that change how we think about space, time, and the very laws of physics. In the search for dark matter, We are not just looking for a missing piece of the cosmic puzzle. We are also searching for the key to understanding the universe itself, how it began, how it evolved, and where it is headed. The discovery of dark matter could reveal answers that we never thought possible, offering a glimpse into the deepest workings of the cosmos. Yet, for all the progress we've made, we are still far from fully understanding dark matter. Every new discovery brings us closer to unlocking its secrets, but it also raises new questions, keeping the mystery alive. And that is what makes dark matter so captivating. It is a force that not only shapes the universe, but also challenges our understanding of everything we thought we knew. As we continue to unravel the cosmic mystery of dark matter, it becomes evident that this elusive substance holds the potential to challenge our understanding of not just the universe's structure, but the very laws of physics. While we know it plays a key role in the formation and maintenance of galaxies, it also serves as a bridge between the observable universe and the hidden realms that remain largely beyond our grasp. Dark matter could be the force that connects everything we know with everything we don't understand, an essential thread that weaves together the fabric of existence. In the search for dark matter, one of the most profound questions we face is, how does dark matter influence our understanding of space and time? The presence of dark matter distorts space-time in subtle but significant ways. Just as gravity bends the fabric of space and time around massive objects like stars and black holes, dark matter's gravitational pull creates a vast, invisible framework that shapes the structure of the universe. What if dark matter is not just a passive force, but one that interacts with the very fabric of reality itself? What if, through its gravitational effects, dark matter influences how time flows across the cosmos? Could dark matter be a hidden force that guides the passage of time, bending it in ways that we can only begin to understand? These questions push the boundaries of physics and invite us to rethink our entire perception of reality. The concept of dark matter also challenges the way we think about the origins of the universe. Theories suggest that dark matter existed in the very early stages of the universe's formation, influencing how galaxies and stars took shape. If dark matter was present from the beginning, could it have been responsible for guiding the early expansion of the universe? Could it have played a role in the cosmic inflation that took place shortly after the Big Bang, shaping the universe's structure and setting the stage for the formation of the first galaxies? As we look forward, we must also consider the potential future of dark matter research. With the advancements in technology, particularly with the construction of next-generation particle accelerators and observatories, we are on the verge of potentially detecting dark matter particles directly. The detection of dark matter could reveal an entirely new chapter in our understanding of physics, one that could bridge the gap between general relativity and quantum mechanics, unifying the two pillars of modern physics. The future of dark matter research is a horizon full of promise, a space where science and imagination intersect. It is a reminder that, despite all we have learned, the universe still holds countless secrets waiting to be uncovered. Dark matter, with all its mystery and intrigue, continues to challenge our assumptions and inspire a new generation of scientists to look deeper into the unknown. As we continue our exploration, we are drawn toward a deeper realization. The discovery of dark matter may not only alter our understanding of the universe, but also challenge some of the most fundamental assumptions about how we perceive the laws of physics. The questions we are asking about dark matter go beyond mere curiosity. They are questions that could radically shift our worldview and reshape our understanding of reality itself. One of the most profound aspects of dark matter is that it exists everywhere. It's not confined to just one part of the universe, but spreads throughout space, influencing everything from the movement of galaxies to the formation of large-scale structures like clusters and superclusters. But if dark matter is so ubiquitous, why can't we see it? What is it about dark matter that makes it so difficult to detect? Scientists have proposed that dark matter could be made of particles that interact only through gravity and possibly the weak nuclear force. These particles, known as WIMPs, weakly interacting massive particles, are believed to be massive but very elusive. Despite this, experiments are currently underway to directly detect dark matter particles, including those at the Large Hadron Collider and in deep underground labs, where scientists are trying to capture the faint signals from these invisible particles. Though no conclusive evidence has yet been found, these efforts continue, bringing us one step closer to identifying the true nature of dark matter. The question of what dark matter is made of brings us to the realm of quantum physics, where the very idea of invisible forces and particles interacting with visible matter challenges our classical understanding of reality. Could dark matter be a clue that leads us to new particles or dimensions, forces that exist beyond the ones we currently know? If so, how would these discoveries change our understanding of space, time, and the fabric of reality itself? As we delve into these questions, we also consider the broader implications. If dark matter exists in such abundance, influencing everything in the cosmos, what does that say about the nature of the universe? Could we be living in a universe that is far more complex, interconnected, and hidden from our view than we ever realized? Dark matter beckons us to explore new possibilities and to embrace the mystery of what we don't yet know. It's easy to become frustrated by the elusive nature of dark matter, but it is precisely because of its mystery that it holds such profound potential. The search for dark matter is not just the pursuit of a substance. It is a journey into the unknown, a quest to redefine the boundaries of science and challenge our deepest assumptions. Each new experiment, each new theory brings us closer to uncovering a truth that could change the course of physics and provide a deeper understanding of the universe's secrets. As we explore the mysteries of dark matter, we come to realize that the journey is not just about uncovering a hidden substance, but about challenging the very way we think about the universe. Every new piece of the dark matter puzzle brings us one step closer to uncovering truths that may radically change our scientific paradigms. And yet, As we continue to search, we encounter something even more profound: the possibility that dark matter might be part of a deeper, more complex framework that governs not just the cosmos, but the laws of physics themselves. At its core, dark matter is not just a question about what is in the universe, but how the universe works. The very fact that dark matter cannot be detected by traditional means, through light, heat, or other electromagnetic radiation, forces us to reconsider what we define as matter and energy. It challenges us to expand our understanding of the universe, pushing the boundaries of physics into realms we have yet to explore. For instance, could the existence of dark matter imply that our current understanding of space-time, our concept of the fabric of the universe itself, might be incomplete? Could dark matter be interacting with the very structure of space-time in ways that we don't yet have the tools to observe? As we investigate dark matter's gravitational effects, we begin to wonder if its influence on the universe could reveal hidden dimensions or unknown forces that exist outside our perception. Some theorists suggest that dark matter could provide evidence for the existence of extra dimensions, dimensions that are beyond the 3 dimensions of space and one of time that we are familiar with. According to string theory, there could be additional spatial dimensions that we simply cannot detect with current technology. Could dark matter be a manifestation of these higher dimensional forces? The idea that we could live in a universe with more than the dimensions we experience every day is a breathtaking thought. And if true, it would not only revolutionize our understanding of dark matter, but of the very nature of reality itself. In a similar vein, the search for dark matter may help uncover a more complete theory of gravity. Gravity, as we understand it today, is still only partially explained by Einstein's general relativity, which works remarkably well on large scales, but doesn't fully account for the behavior of matter at the quantum level. The interaction of dark matter with gravity might offer a bridge between these two realms, quantum mechanics and general relativity, paving the way for a unified theory that explains all forces in nature. For now, as scientists develop increasingly sophisticated tools to detect dark matter, it remains the ultimate cosmic mystery. Its elusive nature invites us to look beyond the familiar and into the unknown, to question what we think we know about the universe, and to embrace the uncertainty that drives the search for knowledge. Every failure to detect dark matter brings us one step closer to understanding the nature of the universe, revealing just how much we have yet to learn. As we journey deeper into the unknown, dark matter continues to beckon us toward a more profound understanding of the universe. Every discovery, every new piece of evidence, brings us closer to unlocking the grand secrets of the cosmos. And yet, as we search for the very building blocks of reality, we come to an unsettling realization. What if dark matter is just the beginning? We are no longer dealing simply with a missing component of the universe. The more we learn about dark matter, the more we realize it might be part of a much larger, more intricate puzzle. It's as if we are standing at the threshold of a deeper understanding of space, time, and the very forces that govern everything we know. Could dark matter be a part of a greater cosmic framework, one that includes forces and dimensions beyond our wildest imaginations? One of the most fascinating aspects of dark matter is that it interacts only with gravity and possibly the weak nuclear force. Yet its influence is felt across vast distances. Unlike ordinary matter, which interacts through electromagnetism and can be detected by light, dark matter exists in an entirely different realm, one that we can't directly observe. This forces us to ask, what other forces might exist, hidden in the universe, that we haven't yet discovered? Could dark matter be a sign that there are aspects of reality that remain outside our current understanding of physics? As we ponder these questions, the possibility of extra dimensions begins to seem less far-fetched. The idea that there could be more than the familiar 3 dimensions of space and one of time is not new. Theories such as string theory have suggested that the universe might have additional spatial dimensions that are imperceptible to us. Could dark matter be a manifestation of these higher dimensions? What if the universe, as we know it, is just one layer of a vast, multi-dimensional reality, where dark matter interacts in ways we cannot currently perceive? One of the most captivating possibilities is that dark matter could be the key to unifying the forces of nature. Gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. For years, scientists have been seeking a theory of everything, TOE, a unified framework that explains all of the fundamental forces. If dark matter is tied to forces that we don't yet understand, it could provide the missing link, offering new insights into how these forces interact. This could lead to a breakthrough in physics, allowing us to see the universe through an entirely new lens, and opening the door to discoveries that could reshape our understanding of reality itself. But even with all of this potential, the search for dark matter remains one of the most elusive quests in science. Its presence is known through its gravitational effects, but its true nature is still beyond our reach. Scientists are working tirelessly, building increasingly sophisticated detectors and experiments, hoping to catch a glimpse of the particles that make up dark matter. In every failed experiment, there is a step forward, a clue that brings us closer to understanding the universe's deepest mysteries. As we continue to explore dark matter's elusive nature, it becomes clear that its discovery is not just a matter of uncovering a new particle or force, but about unlocking the hidden truths of the universe itself. If dark matter is indeed a fundamental component of the cosmos, it suggests that there is so much more to the universe than we can see or measure with current technology. It beckons us toward the unknown, toward a deeper understanding of the forces that govern not only the stars and galaxies, but the very structure of reality itself. While dark matter's gravitational influence has been established, we still don't fully understand its behavior on a microscopic scale. What is it made of? How does it interact with regular matter? And what role does it play in shaping the universe at its most fundamental level? These questions drive the search for dark matter forward, as scientists work to create more sensitive instruments that might one day provide the breakthrough needed to directly detect dark matter particles. However, there's another fascinating possibility to consider. Could dark matter be tied to something even more mysterious? Something that connects it to the very fabric of space-time itself? Some theories suggest that dark matter could be the key to understanding the behavior of gravity on cosmic scales. While gravity is the weakest of the four fundamental forces, it has the most far-reaching effects, governing everything from the fall of an apple to the movement of galaxies. Could dark matter's influence on gravity lead to a deeper understanding of how gravity works in the most extreme conditions of the universe? Even more intriguing is the possibility that dark matter could help explain the nature of black holes, those mysterious cosmic objects where gravity is so strong that not even light can escape. Black holes are known to warp space-time in ways that challenge our understanding of physics, and dark matter may be playing a role in this phenomenon. Some scientists believe that dark matter may contribute to the formation of black holes or influence their growth over time. By studying the relationship between dark matter and black holes, we could gain new insights into both. The search for dark matter may also help us understand the nature of dark energy, the force that is driving the accelerated expansion of the universe. Although dark matter and dark energy seem to have opposing effects, dark matter pulls matter together, while dark energy pushes everything apart. They may be connected in ways that we don't yet understand. Some theories propose that both dark matter and dark energy are manifestations of a deeper, more fundamental force that operates on a cosmic scale, influencing the universe's evolution from its earliest moments to its ultimate fate. As we continue to unravel the mystery of dark matter, we realize that it is not just an isolated question, but a doorway to even deeper questions about the universe and our place in it. The search for dark matter is a quest to understand the very nature of reality, to peer into the heart of the cosmos and uncover the hidden forces that shape everything we see. And in doing so, we may one day unlock the most profound truths of existence itself. As we look deeper into the universe and continue our search for the elusive dark matter, we are faced with the humbling realization that the more we uncover, the more there is to discover. Dark matter, in its quiet, invisible way, holds a mirror up to the universe itself, reminding us of just how little we truly understand about the fundamental nature of existence. One of the most fascinating aspects of dark matter is its relationship to the larger cosmic structure. We've seen how it plays an essential role in the formation and binding of galaxies. But could dark matter also have a deeper, more intimate connection to the very fabric of space-time? Could it be that dark matter is not just some extra component in the universe, but is a central player in the evolution of the cosmos? It's important to consider that dark matter doesn't just exist in a vacuum. It is part of an intricate web that spans the entire universe. The gravitational influence it exerts on galaxies and galaxy clusters suggests that dark matter is intricately woven into the very structure of space. In fact, one of the most intriguing aspects of dark matter is how it seems to work in harmony with the expansion of the universe itself. As the universe expands, the galaxies drift farther apart, but the cosmic web remains intact, held together by the unseen threads of dark matter. Could dark matter be the invisible skeleton of the universe? Just as bones give structure to a living organism, dark matter gives shape and stability to the vast cosmic system. It's not just about galaxies, stars, or planets. It's about the universe as a whole. Without dark matter, the universe would look completely different, and the galaxies we observe today might not exist at all. Furthermore, the mystery of dark matter may hold the key to understanding the evolution of the universe from its birth to its possible end. If dark matter has shaped the universe's growth over billions of years, could it also influence its eventual fate? If dark matter is as pervasive and influential as it seems, could it be the key to understanding the forces that might lead to the universe's ultimate collapse or continued expansion? Some scientists propose that dark matter might even play a role in the Big Crunch, a potential scenario where the universe could collapse back in on itself due to gravity. Others argue that the accelerated expansion driven by dark energy will continue indefinitely. But could dark matter's presence slow this expansion or alter its course? These are questions that dark matter may help answer. But we must continue to look deeper and ask the questions that will drive us forward. The search for dark matter is more than just a scientific endeavor. It is a journey into the unknown, one that may reveal not only the hidden forces that shape the cosmos, but the very nature of reality itself. By understanding dark matter, we may unlock the key to understanding the universe's past, present, and future. As we continue to explore the profound mystery of dark matter, it becomes increasingly apparent that its influence stretches far beyond what we can observe or measure directly. For years, scientists have been piecing together the cosmic puzzle, and with each discovery, we are learning more about the invisible hand that guides the formation of the universe. But dark matter is not just a force that holds galaxies together. It may also offer the answers to some of the most profound questions about the nature of existence itself. One of the most striking aspects of dark matter is its ability to remain hidden in plain sight. Despite its gravitational pull on visible matter, dark matter does not interact with light or any of the other electromagnetic forces we are familiar with. This means that unlike the stars and galaxies we can observe with our telescopes, dark matter cannot be seen or detected by conventional methods. Yet, it exerts such a profound influence on the universe that we cannot ignore its presence. This raises a fundamental question. If dark matter is the missing mass that holds galaxies and clusters together, why can't we directly observe it? How can something so important remain so invisible? Some scientists speculate that dark matter may interact with ordinary matter in ways we don't yet understand. For instance, could it be that dark matter particles could occasionally interact with each other, but at such a weak level that we have yet to detect it? Or could dark matter be composed of entirely new types of particles that interact with known matter in ways that break our current models of physics? The search for dark matter is, in essence, a search for new physics. As we build more sensitive detectors and observe more distant parts of the universe, we begin to realize that the properties of dark matter could revolutionize our understanding of the laws of nature. Could dark matter lead us to discover new forces, new particles, or even new dimensions of space-time? The more we learn, the more we see that dark matter is not a simple problem to solve, but a key to understanding how the universe works on the deepest level. For instance, one of the most exciting areas of dark matter research involves the potential connection between dark matter and the theory of supersymmetry. Supersymmetry, a theory that extends the standard model of particle physics, proposes that every particle we know has a corresponding superpartner particle. Could dark matter be made of these superpartner particles? If so, detecting these particles would not only provide evidence for dark matter, but could also offer a breakthrough in understanding the fundamental nature of the universe. There is also the possibility that dark matter could help us unlock the secrets of gravity itself. Gravity, as we've observed, is the weakest of the fundamental forces, yet it dominates the cosmos on the largest scales. Could dark matter provide a new understanding of gravity, one that could reconcile the forces of quantum mechanics with those of general relativity? If dark matter is indeed the missing piece of the puzzle, it might offer a new perspective on the most fundamental force that governs the universe's structure. In many ways, the search for dark matter is a journey not just into the cosmos, but into the very heart of reality. It forces us to confront the limits of our current understanding and invites us to think in new ways about the nature of existence. The answers to these questions could fundamentally alter the way we view the universe and our place within it. As we approach the final leg of our journey into the mysteries of dark matter, it's clear that its significance stretches far beyond its gravitational influence on galaxies. Dark matter is not just a cosmic oddity or an enigma waiting to be solved. It is the key to unlocking some of the universe's deepest and most profound secrets. With every discovery, we are slowly but surely peeling back the layers of reality, revealing a universe far more complex than we once imagined. We've explored how dark matter holds galaxies together, shapes the cosmic web, and could even help us understand the nature of gravity itself. But as we close in on the potential answers, we're reminded that science is often a journey into the unknown. What we know about dark matter today is still just a small fraction of what we need to understand. And that is what makes the search so thrilling. Each new discovery opens the door to countless more questions. Could dark matter hold the key to understanding the very nature of space and time? The fact that dark matter interacts with gravity but not light suggests that it operates in ways we don't fully comprehend, potentially influencing the structure of the universe in ways beyond our current models. As we study dark matter, we may find that it's not just a hidden substance, but a window into new realms of physics, areas where space and time are not simply passive entities, but active players in the cosmic drama. Moreover, The search for dark matter challenges us to reconsider our place in the universe. For so long, we've thought of ourselves as the center of our cosmic understanding, with the laws of physics carefully defined and well understood. But dark matter reveals that our knowledge is incomplete, that we are still only scratching the surface of a universe that is much larger, more mysterious, and far more interconnected than we ever imagined. Could dark matter also shed light on the big questions about the universe's origins and ultimate fate? If it played a role in the formation of the first galaxies, stars, and even black holes, could it hold the key to understanding the ultimate future of the universe? Whether it will continue to expand forever or eventually collapse into a big crunch. These questions, while still speculative, highlight how much dark matter could teach us about the cosmos's grand design. As we move forward in our exploration of dark matter, we stand at the precipice of a new era of scientific discovery. The mysteries of dark matter are still largely unsolved, but with each new experiment, each new theory, we are inching closer to uncovering its true nature. What dark matter reveals will not only shape our understanding of the universe, but will likely lead to a new chapter in physics itself, offering us a new lens through which to view the cosmos and our place within it.